So hello everyone, I will present the project 4, which is about understanding industrial processes, dynamics through AI, and it will be about a reactor process. Yes, it's not easy without the maybe. Okay, so what about the context? In fact, in our society, we have more and more industrial processes which are quite complex. So complex that even the industrial not fully understand its own process actually. So typically we have like non-linear dynamics and high coupling between several subsystems in the process. And so it's highly complex, and on top of that, we have often a control which is in place, which is often based on PID, but it works better. It's better suited actually for linear systems, and all the time it's not the case. It's highly non-linear systems. And we have, in addition, some uncertainty, disturbances, force, and so on. And so we come to suboptimal operation actually, suboptimal control, and so economic losses. And so we have more and more industrial which are interested to optimize their control. And the good news is that regarding machine learning, there are more and more solutions that are developed in this domain, so for industrial processes. But the problem is that when we come to industrial use case, we have the trust gap in the sense that we really need to convince the operators of the industrial company that the machine learning solution that we are trying to put in place can be trusted, can be understandable, can show some causal insights, and also that it shows some consistencies with physical knowledge, because if you do not give that, the operators will not be convinced to use your tools. And also, if the products that is obtained at the end of the process need really to be highly reliable for the final customer and so on, you really need to demonstrate that some reliability and trustworthy, of course. So we need industrial AI that is trustworthy, interpretable, and accurate. And so it's really the context of this project. So what we will do, we will try several methods, going from the more, I will say, black box methods, but with some explainable methods on it. So like Shapley coefficient, for example. Then we will try also to explore intrinsically interpretable models. So we just talked about Kolmogorov-Arnold's networks in the past project. It's one example of this. And then we will also explore causal modeling and physics-informed neural networks. What will be our use case? We choose one use case that is really well known in the literature actually, which is the Tennessee-Eastman process. It's a chemical process in which we have actually two products, two liquid ending products coming from several gaseous components. And in this case, we have 41 measured variables, 12 control variables in this process, so it's quite already complex. And we have a good sampling frequency around each 3 minutes. And what is really nice is that we have also example of normal operations and faulty operations. And as I said, it's a really widely used benchmark. So if you look about this dataset, you will already find some a lot of papers actually on the dynamics of this process and so on. So it's quite, we are not starting from scratch. And so yeah, the goal of this project will be to develop, compare interpretable, causally meaningful and physics consistent ML models for better monitoring, control, and advanced digital twin development industrial environments. It's the final goal, not for this workshop, but it's the final goal. And so we have quite already a nice team, so it's already multi-institutional actually. So me, Noémie Vlaminck, I'm the team leader from Seneco Research Center. My expertise is more about time series forecasting, manufacturing data analysis, and before I have also done some speech and image processing. In our team, we have also Cyriac Deli, which is a PhD student at Liège, and he's doing a thesis really on this topic, so on studying dynamical system, which may be complex and in an industrial environment. And he has already worked on neural differential equation, for example. We have also Eizu Ozen, which is one of my colleagues at Seneco, which has expertise in multi-fidelity, reduced order modeling, and digital twin. And finally, we have Zaha Zamanian, which is from Le Mans, and he is doing a PhD student on battery management systems. And she is really an expert in dynamical system control. So we have quite already a nice team. For the work plan, actually, depending on of course, on the number of people and so on, we'll not do everything. It will depend on the number of people. But in the ideal case, what we can do is starting from, of course, exploring the data sets, and then doing some silly black box basis to compare with more explainable methods afterward. And then we will add interpretability, then add causal modeling, then try some simple physics for model and so on. It really depends on the expertise of people and the number of people we are. So what we are looking for people expertise, so typically people that are interested to go beyond black box model and find a way to explain their model, or even going to physics informed model. So yeah, the three main expertise topics, they explainable and interpretable AI, causal machine learning, and physics informed AI. And yeah, do not hesitate to join us if you are interested, and do not hesitate to ask questions.
Any question?
I have a question.
Yeah.
Just a question for the purpose and the goal. Is it like anomaly detection or more of a prediction or something like that?
I think, yeah, it's more about find a way to modelize the dynamics. So it's kind of a system identification. And then one of the first, I would say, use case linked to that is time series. It's more about time series forecasting. So trying to predict the future of the process dynamics. For me, anomaly detection and also control, it's beyond, it's the next step. And so I don't think that during the workshop we will go to anomaly detection and putting control in place. Just trying to identify the dynamical system and trying to predict its future.